So yeah, okay. Did you have a question, Vanessa?
So basically screening is like all those electrons shielding the valence?
Yeah. So, and even electrons within the same subshell will screen each other out a bit, or within the same shell. So let's just say, for example, you have a 2s electron and a 2p electron. They're going to compete for that nuclear charge, and the 2s will shield out the 2p a bit more, right? So what shielding is they are electron-electron repulsions that distort the energy levels, as we talked about multi-electron atoms versus single electron atoms. So you have more of this electron-electron repulsion causing, as you go up the column, you've got less of that because there's simply less core electrons there repelling the outer valence outward. And so, as a result, even the valence electrons are closer to the nucleus as you go up the column. So a 3s1 electron is relatively close to a sodium nucleus relative to a cesium 5s1 electron, which is much further out from the nucleus because of the extra core electrons there. Okay, and then of course going to the right, you've got more nuclear charge. So yeah. So fluorine would be like one of the highest ionization energies. It's like Hugh Jackman. All right. So okay, he's Wolverine. Come on, guys. Okay. So we're going to use this trend now to do some examples. Let's arrange the following in order of increasing ionization energy. All right, so you got silicon, fluorine, indium, and nitrogen. So let's go ahead and draw a trend. So I always recommend doing this. Go ahead and just draw the trend. All right, increasing ionization energy. So where is silicon in this chart? Left, right, up, down. Right, and kind of sort of up a bit. It's like here, right? Here's silicon. And you have fluorine. Where's fluorine? It's even further up, right? So it's one row above and in the corner. Okay, and then you've got indium. Where's indium? It's sort of a little bit below and to the left of silicon. So here's indium. Okay, and then you've got nitrogen. All right, so nitrogen is it's above silicon, kind of like right there. All right, so. All right, so arrange them in order of increasing ionization energy. Which one of these elements has the lowest ionization energy based on the trend? This guy, followed by him, followed by him, followed by him. Okay. Do you think it's a lot easier doing this chart and then just like superimposing them? I think it helps you see it, right? And seeing is believing, right? Okay, so putting these in order of increasing ionization energy, you got indium, in order of increasing ionization energy. Conversely, how would you order these in terms of size? It'd be the opposite, right? The indium should actually be the largest atom. So the two go inversely to each other in general. The larger an atom is, the more screening you have, the easier it is to pluck off an electron when you want to ionize it, right? So the two are sort of opposite. Okay, so here's a chart I want you to know. I really like this chart because it shows a lot. So what you have in this chart is you have the entire, well not the entire, but many of the elements in the third period of the periodic table. So what you have here is you have the elements, and you have ionization energy 1, ionization energy 2, 3, 4, all the way up to ionization energy 7. And when we look at sodium going to argon, in this table, it's going down in a row, but remember, in the periodic table, this is a column, but in the periodic table, this is a row. So you're going from sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. All right. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay. Look at what does ionization energy 1 mean? What does this mean? If I wanted to draw a reaction showing this process, what would it be? So if I'm going to take sodium and I'm going to ionize it, it's going to go from sodium neutral to what? Na plus. Right. Why is it plus charged? Because I lost an electron. Okay. So this would be a way of writing ionization energy 1. What if I was going to write a process for ionization energy 2? So ionization energy 2 means you're pulling off a second electron away from sodium. So if I'm pulling a second electron away from sodium, what it means is I'm taking sodium plus 1 and I'm turning it into sodium 2 plus. And I'm removing that second electron. Okay, what if I did ionization energy 3? All right, let's pick another one that's on here. What if I did chlorine and I did ionization energy 7? What if I did IE7 for chlorine? What would that look like? Cl6 plus going to Cl plus 7, right? Plus an electron. I like writing the number first, then the charge. So do you understand what these numbers represent? Okay, what you're looking at here. So whatever the ionization energy is, there's a number associated with it. The units on this number are in units of kilojoules per mole. So if you wanted to ionize 6.02 times 10 to the 23rd atoms of sodium, it would require this much energy to do that. Okay. So here's what I also want you to notice. As you're going up in ionization energy, like let's take phosphorus. As you go from IE1 to IE2 to IE3, what do you notice? What are the numbers doing? They're increasing, right? So with each successive electron you're pulling off, you have to put in more energy to do that. Why? Why do you have to do that?
It's getting smaller.
It's getting smaller, right? So you're pulling more electrons off. The atoms getting smaller. That means the distance between the electrons that are left are closer to the nucleus, right? And when opposite charges get closer and closer together, it's like pulling me away from Hugh Jackman. Okay, it gets harder and harder and harder. Okay. The other thing is that if you think about it, if chlorine is a +6 and you're trying to pull another electron off of that, versus if chlorine was just neutral, okay, it's just harder to pull electrons off of things that are already positively charged, right? And the more you increase that positive charge, the harder it gets, okay? So the numbers will increase as you're pulling off successive electrons. So keep that thought, and let's do an example. Okay, so arrange the following in order of decreasing ionization energy. So we have bromine, argon, argon plus, and chlorine. So, in order of decreasing ionization energy. So let's go ahead and draw the trend. This is increasing, okay? Where does bromine fit into this picture? Kind of, sort of, like to the right and then middle. And then where does argon reside? Yeah, up here, right? And then you look at, we're going to ignore argon plus for the moment and just look at chlorine. It's going to be above bromine. Oh, this is too easy, right? Okay. So in order of increasing ionization energy, how would you list them? Bromine, chlorine, argon. In decreasing order, how would you list them? Reverse it, right? So in order of decreasing ionization energy, it's argon followed by chlorine followed by bromine. Decreasing IE. When we say decreasing ionization energy, we're talking about in decreasing order of IE1. Okay, the first electron being removed for all these. Okay, so now what about the argon plus? How does that compare to any of these? And this is where I had switched in my mind, you know, comparing argon plus versus potassium to potassium plus for radius. If we compare the neutral argon to argon plus, which one would be harder to ionize?
Argon plus.
Argon plus, right? I mean, if we take argon neutral and turn it into argon plus, and if we wrote IE2 for this, it'd be argon plus to argon 2 plus, right? Clearly, ionization 2 is always going to be higher than ionization 1, all right? And that's what we're asking. So where does argon plus go in this order? So remember, decreasing order, bromine is the easiest to ionize, argon is the more difficult one to ionize. So argon plus is even more difficult to ionize, right? Make sense? So this is the concept of successive ionization energies increasing as you're trying to pull more and more electrons off. Something else I want to point out, okay? And this is more, so this is more of a quantum mechanical thing, okay? A little more nuanced. Sodium, magnesium, so notice how as you go up and to the right in a row, so these are all in the same row. If they're all in the same row and they go to the right in that same row, the ionization energies should just always increase according to the overall trend. But let's look at the numbers. For IE1, 496, 738, okay, magnesium is more difficult to ionize than sodium, it's got a greater charge in the nucleus. Aluminum then goes down. Hey, what's going on here? Then silicon goes up again, phosphorus goes up again, even from silicon. But hey, wait a minute, sulfur goes down. What's causing that momentary downtrend in the ionization energies as we go across the row? What's going on there? And then we go back up again for chlorine and for argon. What is it going from magnesium to aluminum? What's going on there? What was that? You're adding an orbital. Right, so here's the quantum mechanical aspect of ionization energy. So if I'm going from 3s2 and then I've got 3p1, right? So here is aluminum. All right, and here is magnesium. So aluminum, why is it easier to ionize aluminum relative to magnesium? All right, aluminum has the greater nuclear charge. You'd think it'd be harder to ionize it, not easier. But here's where the quantum mechanics comes in. By removing a 3p electron, you're actually reducing the energy level of the valence electrons for aluminum plus. Right, so in other words, aluminum wants to lose this 3p electron more easily than magnesium wants to let go of one of its 3s electrons. Right, by taking a 3s electron off of magnesium, you're going to have disrupting that full subshell that is the 3s. Am I making any sense at all? All right, so if you write this, if you were to write this for argon, I keep saying argon, aluminum plus. Aluminum plus is now saying, yeah, good riddance, I got a free subshell now, it's not even filled. Great, okay? Whereas magnesium plus is kind of like saying, hey, I had a nice 3s filled subshell, and now I've only got one. All right, would you rather have a full glass of beer or a half glass of beer? Depends on who you are. Do you like half glass full, half glass empty? I don't know. It turns out half shells aren't too bad either, though. Okay, if you look at phosphorus, it goes down to sulfur, right? So why is it easier to ionize sulfur relative to phosphorus? Okay, so let's look at the valence configuration for that, or orbital diagram. So phosphorus is what? What is phosphorus? It's 3p3, and how do we fill in those electrons? One on each orbital, right? That's the favorable way of filling, according to what rule? Do you remember the name of the rule? Starts with an H. Hund's rule, right? Okay, so and then we have sulfur. Looks like this. Okay, what about going from sulfur, what about going from phosphorus to phosphorus plus? So by going, if you're going to P plus, you're taking off one of these 3p electrons. Okay, you're not disrupting that nice half-filled shell. Okay, it's like saying, okay, Mr. Fernandez, you have a half glass full of beer, and then now you have only a quarter. And I'm like, hey, wait a minute, I gotta know what to do now. I'm a little bit indecisive. Do I just finish the half shell off, or do I fill up my shell again? I don't know. Okay, or it could be a soda, maybe not beer. But okay, yeah, just saying. Okay, for sulfur now, what happens to sulfur? Sulfur plus, I get 3s, 3p. If I look at sulfur and I take off an electron, that goes from a slightly half-filled, or past half-filled, to now being perfectly half. Okay, this makes sulfur just slightly happier. Okay, does that make sense? So full shells are favored, or full subshells are favored, and full half or half subshells are also favored. So this is why you see this trend in the numbers. So it goes down, and then it goes back up again until it goes down again for that half shell marker. And it goes back up again. All right. Okay, so let's just do one of these, then we can move on. Yeah. Yes. Oh, sorry.
So you're saying that it's either half or full fill? There's no sort of concept, right?
Yeah. So I mean, in other words, sulfur is more willing to give up one of these 4 electrons in here if it gets to be a half after you remove it. Okay, phosphorus a little less willing to give up an electron because it's already at the half subshell mark. It doesn't want to disrupt that. Okay, it's more, more favorable to keep a half. Okay, there's yeah, half is better, full is better. Okay, let's just do the second one here. Use orbital diagrams to explain why sulfur has a lower ionization than, oh, we already did Alright, well that's this one. Okay. And aluminum and magnesium, oh, I already did it. Okay, I forgot I had these. Alright, so we just answer these. Okay. So, if you look at the reactivity of the alkali metals in water, this is a really nice example of how the alkali metals react according to the quantum model. So if you look at lithium, sodium, potassium in the order of the alkali metals, you'll notice that when you throw a pure alkali metal in water, for lithium it reacts pretty violently and you form a lot of gas. Sodium even more, potassium even more. What gas is being produced here, by the way? Let's just see if you remember your redox chemistry a little bit. All right, if I throw in sodium into water, what do I get? Do you remember? Yeah, I get hydrogen gas, and I get the hydroxide salt of that alkali metal. Okay, and the delta H for these are quite exothermic. Okay. Why does potassium react more violently with sodium? It's just the valence electrons of potassium are shielded more, and so they're easier to remove. All right. So as you go down a column for the alkali metals, the reactivity increases. Okay, and it's all explained by Coulomb's law and the quantum model. Check out this video.
They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen. But this time, corrosion occurs even more quickly.
Easier to iron.
The next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with
kind of
air.
dry.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge.
They're kind of old school with the equal sign there. Is it an
Now for
arrow?
potassium.
No.
This time you'll see a blank. The
That's
heat
why they
given
call them
out by the
chemical
reaction is
equations.
produced so quickly that the hydrogen gas catches fire. It burns in a light flame. The next element is from video. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group.
Terrifying.
That is alkali metal.
Alright. So, yeah, they become more terrifying. Those are fume-hood affairs for sure. Okay, so that's ionization energy. Last one I want to talk about is electron affinity, otherwise called EA. So, electron affinity is the propensity of an atom to gain an electron. I'd like you to amend this for a little bit. So it just says here the propensity of an atom to gain an electron. Let's be a little more clear. It's the propensity of a free gaseous atom to gain an electron. This is different from a term called electronegativity, which we'll talk about next chapter. All right, so I would just add the words propensity of a gaseous free atom to gain an electron. Okay. So electron affinity increases. When we say that electron affinity increases, it means that electron affinity is becoming more negative because the energy is released when an atom gains an electron. Question?
I've never heard the word propensity.
Propensity means likelihood, right? So the likelihood, it's the likelihood of an atom to gain an electron. So the more exothermic the electron affinity is, and remember exothermic results in a negative delta energy, the more negative it is, we say that that's the electron affinity increasing. Okay, it's becoming more negative. Okay, it's increasing in its negativity. Why are electron affinities often negative? Well, if you think about it, you've got a proton with a positive charge. If you throw an electron onto it, it's like bringing a negative and a positive charge closer together, and there's a potential energy that's met when that happens. Okay, it's like having a long distance relationship. Someone you're dating is over in New York, you're here in Los Angeles, and then they come visit you. How do you feel? You feel more relaxed, you feel happy, okay? That anxiety went down. Well, guess what? When opposite charges want to come together, when they're farther apart, there's like this anxiety there. And then they come together and it relaxes. And there's energy that goes out into the surroundings, and that's the potential energy being released out into the surroundings when that happens. And so with electron affinities, that's what you're looking at with the negative sign on a lot of these. So in general, electron affinity increases, becomes more negative as you move up a column or to the right in a row. So it's very similar to ionization energy. It's increasing as you go up a column or to the right in a row. But in this case, it's becoming more negative. And it also depends on the half shell, full shell concept. Okay. So it's very much like ionization energy, up and to the right. Okay, as you're going up a column, the increasing electron affinity is there because there's less screening. Okay, in other words, as atoms get smaller, there's less core electrons blocking potential electrons that are going to be gained from getting into the atom. Okay, again, it goes back to, okay, I want to drink, I want to go to the bar, I'm parched, I need a glass of water. Okay, there's too many electrons in my way, I can't get there. Okay, but the smaller the atom gets, the more you can get to that glass of water. Okay, and then again, as you're going to the right, the electron, the nuclear charge is increasing. So again, that's like saying, okay, I've been dying to meet Hugh Jackman my whole life, and I finally get to meet him. And all this potential energy is released out because now I'm so happy and relaxed to meet Hugh Jackman, right? So as you're going to the right, the nuclear charge is increasing. Hugh Jackman has a very high nuclear charge, okay, by analogy, okay. Yeah, okay, hopefully we'll get over that someday, all right. My wife likes him too, okay. So let's arrange the following in order of increasing electron affinity. So all these elements, they're in the same row in the periodic table, right? You got silicon, chlorine, magnesium, okay, they're all in that third row. Let's arrange them in order of increasing electron affinity. Yeah, so electron affinity, if you have an affinity towards something, it means you tend to want to go towards it. It's like attraction, right? You know, so it's a measure of how much electrons are attracted to an atom, to a free gaseous atom.